I've got coffee everywhere. That's disturbing. One moment, please. All right, so let me see. What do we do derivative for? Why do we use these? Thanks. Connor, I'm going to you next. So, why do we? What? Define. Say it. That's right. That's right. So derivatives, yes, are slopes. Awesome. And so we can do a lot of things with them. So Connor, why specifically would I, if I had, here's a graph, yay, whatever, take the derivative of this graph, whatever, and if a person were to sketch that derivative, because it totally could, where would you start, Connor? Where would you start if you were going to sketch its derivative? There is a right and wrong answer here, so I will not be saying you're not wrong on this problem. Because you might be, or you might be wrong, or you might be right, but you're not going to be not wrong.
Well, at first I was going to say this on like one of the maximum.
Oh, right here? And what about it? What's the slope there?
0.
I feel like it is too. Good job. And here. And here. Beautiful. Oh, shut up and go away. Nobody cares about you. And then what would you do?
I would get the 0
Well, I feel like over here these are positive slopes, aren't they? Over here, this side over here, they're positive slopes. You know what I'm saying? So I feel like I'd probably graph them like this maybe, eh? Because they're positive. And then the slopes go negative, don't they? Mr. Grimm has a question for Lily. Lily, between this maximum and this minimum, where is this graph of the steepest slope? Is it here? 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 Where is it the steepest?
Yes, in the middle.
Like, right there? So on this sketch, you see, of the derivative, shouldn't it go down to the bottom? Shouldn't it be like right under the steepest part of that curve? Right? Because that's when it was going down the steepest. And then it's still negative, but it's coming back up because these are less negative than it was here. Huh? Got it? Huh? And then right here somewhere-ish, well-ish, maybe in here-ish, is where the maximum steepness part is, right in here-ish, maybe. And then down here like so, and then, dude, this sucker drops like a rock, don't it? You see what I'm saying? Because that is pretty steep. Almost vertical, but it's not. But we go way down there, yeah? And so, yeah, everybody's happy about that. But, Nathan, question. Suppose one were to sketch, because, oops, wait, let me go back. Because remember, this is the first derivative. But could a fella, or a lady, or heck, let's not even be binary. Could a person, probably not a dog, but could a person sketch the second derivative? That is, the derivative of the derivative.
Yes.
I feel like they could. Yeah. And how would one do that, if one were to do that?
Take the maxes and
No, I know! What? And then these are what kind of slopes over here, this red line at first? What's it doing? Well, it's coming down. So it's got negative slopes because it's coming down. And then it's coming back up. So, and again, right in here is probably the steepest. It doesn't ever go very steep at all, does it? And then so what happened here? Oh no, there it is. I was looking at the wrong curve. I was looking at the black curve. And then the red curve goes down again. Like so, eh? Something like that. And a fella could, or a lady, could do this all day. Couldn't one? I feel like we could. I feel like it'd be pretty easy to do. Brooke, the next one is all yours, sister. Brooke, what if I had this function? And this is f of x. What would the first derivative of this thing look like, Brooke?
Well,
Where would you start if one were sketching it?
no.
I would too. Because it's got zero slope right there. You're not wrong. And then, but how do I graph this doohoo? What kind of slopes we got going on over here? What are these kind of slopes? They're positive or negative initially? Over here.
Negative.
Well, these are all positive slopes, aren't they? They're going uphill?
Yeah, I couldn't see because like
I feel like it's going uphill, so something like that. Now, physics people and former physics people, pay attention to this. Huh? Huh? Except these would be functions of t, of course, but you get the picture. Oh my gosh. What would f prime of t be? Negative 9.8 t plus 50, right? You're like, I don't have physics, so I don't know what you're talking about. This doesn't matter, I'm just saying. That's a linear function, isn't it? Where would this thing equal 0 at? I don't know. Wait, yes I do. 9.8t would equal 50, and so t would equal like 5.1 or something, right? Where does that happen? Right? Ish? Yes? Now Brooke. Brooke, dear Brooke. Dear Brooke. What if I wanted to find f double prime? But Mr. Groom, the red line is a straight line. That's a linear function. The derivative of a linear function is just its what? What's the slope of this fella right here, by the way? I know! It's negative 9.8. F double prime. But it's it's constant. That's right. Why is it down there, Mr. Grimm? Because it's always negative. Does the first derivative have a maximum in the true sense of the word? It does not. It's linear. So that's what it's going to look like. And we can do this all day long. Calculus people, of course, you're going, wait, that's right, because like gravity is like constant. I know. That's right. Yeah, that's right. And so you remember, like, well, for instance, the definition of acceleration is the change in v over t. Well, that's exactly what we have right here. That's what this thing's telling us. So there's your acceleration times time plus your initial velocity equals final velocity, kind of a deal. Oh no! But that's like the derivative of this. How about that? Because the change in distance is velocity. Yes. Nice. And so we're going to look at them, and most of what we're going to do today is a whole bunch of how-tos. So we'll sketch a few. I think we've sketched enough. I feel like we've sketched them until we're blue in the face, pretty much. But suppose you had f of x. Well, I don't know, 14x squared plus 6x minus 1 e to the x or something, I guess. Why not? Because I felt like it. So the first derivative, of course, is just what? 28x. Bam. And of course the second derivative is just the derivative of that, which would be? I know. Hey, let's go more. Could I do the third derivative? I suppose. No. Mr. Groom, the fourth derivative. This is ridiculous. Should I use Roman numerals? No, you shouldn't. What the big kids do is this. And of course the answer is simply negative e to the negative, or negative e to the x rather. Ta-da! And you could keep going, right? Would this one ever go away? No. Some functions will go away, some will never. Like the sine of x. Could I take the 22nd derivative of the sine of x? Yes. What will it be? Negative sine. How do you know? Because there's a pattern. Okay. So a fella could, or again a lady, whatever, could say, well, Mr. Groom, I feel like f of x is, here we go, 6 sine x. Tricky dicky. So what would the 22nd derivative be? Oh no. Well, I know this. It's either going to be this, or it's going to be this, or it's going to be this, or it's going to be this. It's going to be one of them, yes? Right? So let's count it out. This is the original function. The original. So first, second, third derivatives. Fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12, and so forth and whatnot, yes? So every multiple of 4 we're going to have an issue, yes? So the 20th would put us back up here, yes? Would be the 20th derivative. So the 22nd would be this fellow. You should take advantage of those sort of patterns whenever possible. One should not try to do that 22 times. One will get lost, probably. Okay. The good news is when it's a sine function or a cosine function, it's not that hard to do. It's really not. What does the 22nd derivative mean? I don't know. Second derivative, I know what it means. It means acceleration, for instance. It means the change of the change. We'll use some other stuff with it later on. Third derivative, one or two little piddly diddly uses, but not too much other than that. And after that, we're not going to do much with them except, what if you had a gross function? What if you had an absolutely gross function, but you could create a function that looked just like it, that was a polynomial? That is an x to the 5th plus x to the 6th plus x to the 4th or whatever. Wouldn't it be so much nicer if it was a nice polynomial? We like polynomials. They act nicely. They behave appropriately. Because when you... excuse me. Because when you take derivatives of polynomials, what do you get? Well, polynomials! They're so easy. It's not like it's some gross mess. It's nice. So there is one thing we'll do later on. We will do not 22nd derivatives, but like 5th and 6th maybe or something, but nothing much more than that. If you had to do much more than that, one would get a computer and do it for them. Okay? But yeah, whatever. So, a couple of things. Today you will see this. So of course we use this formulation. So f prime, as I said, f double prime, sure. And then after that, usually the big kids switch it over about 3. Sometimes they'll do 3 marks, sometimes they don't. And then after that, it's pretty much and so forth and whatnot, okay? Also, we'll write them this way sometimes, and we'll write dy dx, and then we'll write d squared y over dx squared. And then I keep going like this. Leibniz notation is nice for some things. I find it a little obnoxious when I'm taking multiple derivatives, like second, third, fifth derivatives. I find it annoying. If it's first derivatives, I kind of like it. Dy dx, I mean, that literally is, that is changing y over changing x, which is the definition of slope, which is kind of cool. Okay. Could have also have written it as y prime, y double prime, y triple prime, and then usually again, same kind of basic procedure as such. Some books will write it like so, and so forth, which I always found annoying. Literally, there's a million ways to write them. The big ones, though, are f prime and dy dx. Those are the biggies. Okay? I don't really care as long as you understand what the book is asking you to do. Then I'm pretty happy about it. Okay? For instance, they could ask you this question. I'm going to die. No, here's what they might ask you. Let's do this one. Yes. Yeah, whatever, dog. Boom. What do they want from me? Don't they want a third derivative? Yes? A third derivative. So if I want a third derivative, I better go find the first one first, yes? So the first derivative, and I'll probably write it, if it was me, I'd probably write it like so. But I'd write it. Here it is, the first one would be 6x plus 6. What is the derivative of that mess? Well, I don't know, but isn't it 1/7 x to the 1/2? Right? So that's 1/14 x to the minus 1/2. And then it's minus 7 cosine of x. Okay? That's nice, but that's not the answer, so that's just an intermediate step. Don't stop there. So the next one is... What's that? What's the next one? Did you say 6?
No.
6? And then what? 6. So 6 minus 1/28 x to the negative 3 halves. Then what? Plus or minus? Plus 7 sine x. I thought cosine went to minus sine. Well, it does, but it's already minuses. And then third derivative, here we come. And here's our answer. So our answer, of course, is going to be positive 3/56 x to the minus 5 halves plus 7 cosine x, which then a normal person might choose to write thusly. I didn't say that you had to be normal. I just said a normal person might write it that way. Hannah, on the original function, is there anywhere where this function does not exist, dear? In the original function?
Is there anywhere it doesn't?
The function does not exist, yeah. What's the domain of that function, in other words? Everybody has a domain.
For reals?
Can I square root -7?
Non-negative.
Non-negatives. Props to you. That's the way to save it. Good job. And we would say that it is right continuous at 0, yes? Right? So as you're coming into square root to x, coming into 0, everything works, yes? But it's not continuous at 0. It's right continuous at 0, yes? It just bursts onto the scene at x equals 0, yes? Nice. So that's a true statement. I like that. Good job. Nice. Look down here. What is this thing? Does this guy have any issues? Does he have any issues at x equals 0, for instance? I feel like x cannot be 0 down here, can it? X better be positive, yes? Straight up positive. Now, why is that? Why is that? Because if it just showed up on the scene, how much did it increase by from where it wasn't to where it is now? Yeah, it's infinite, yo. I can't do that. Okay, so that's why it's got the asymptote there at 0. You're always going to keep bringing that up. I cannot stress. I'm going to tell this out. I'm going to keep drinking. Then I'm going to get a tummy ache. You cannot stop ever. You can never not talk about where things are differentiable or where they are, where they're continuous functions. That's always going to be a thing in calculus. Always, 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 always. Never will there be a time when it's not a big deal. Now, on page, this is section 3.5 is where you're going to be doing some of these problems. And you might see one of these show up as well, for instance, hypothetically. D, dt, there we go, like so. And 3t squared plus, why am I doing squareds all the time? Here, if Levi was here, this would really piss him off. Yeah, here we go. Sine x, sure. Ooh, that would have freaked the kids out. Plus e to the pi, sure. And I want for t is equal to 0. No, that's boring. T equals pi, sure. Nice. So it wants me to do the second derivative, and then what does it want me to do? Plug a pi in for t eventually, yes? So second derivatives first, what do you get? What's the first derivative? What is it?
16 plus 14 plus 6 cosine.
Cool. Wrong! Ha ha! E to the pi, friends. What is it? It's a constant. Just want to see if you're paying attention. E to the pi, what is it? It's a constant. What's the derivative of a constant? It is 0. How fast does a constant change? Yeah, it doesn't. So it's 0. Just trying to see if you're paying attention. That's good. It's a learning thing. It's alright. Now, y double prime is what? 6 plus 12t squared minus 6 sine. So let's slap in the old pi. You get 6 pi plus 12 pi squared. And what's the sine of pi? What? Say it again. It is 0. Hot dang. Yay. What? What? Did I mess something up?
Yeah, the second derivative, you put 6 plus 12 t squared, but I think you plugged in pi for because you thought it was t instead of plus for the second derivative.
6 plus, so it's 6 pi. It's 6.
Thank you. Thank you. Can't even read my own freaking handwriting. By the way, here's a question for you. Y prime at pi, is it positive or negative? Feel like it's positive because this is positive and that's positive, so it's positive, yes? That's going to mean something to us the next day or 3. You with me? This is not right today, but that's going to mean something to us. Obviously, it's a number, obviously. Pi squared is 9-ish, times 12 is 108-ish, plus 6 is, let's call it 120-ish when we're all done, okay? That's positive. So what's that going to mean to me in a couple of days? It's going to mean something, but not today. It's simply a matter of plugging it in and evaluating it, okay? Now, later on, what we're interested in is frequently we're going to be interested in when is my derivative equal 0, yes? That's frequently what we want to know. Well, we also want to know that with second derivatives too, frequently. And we're interested in when they're positive, when they're negative, and when they're 0, because it's going to mean something to us. Today, we're literally just going to crunch them because it's kind of fun. Okay? Oh, I changed my mind. I'm going to teach you a little bit about it. Now, here's our good friend x squared. We love him so. What is y prime of x squared? And what is y doubly prime? Los. Wait, Mr. Grimm, I know what x squared looks like. It looks like this fella. You're not wrong. Good, good. Hey, look, Mr. Grimm, at x equals 0, we have a minimum. Well, duh, because that's where this fella equals 0, yes? Interesting to note, just curious. This graph, notice how it always opens up like this. You see that? We call this concave up. And we call this one concave down. And the game is this. When you take the second derivative and put it equal to 0, we call this a point of inflection. And that is where it changes from being concave down, let's say, to being concave up. So right here, where it changes, it would be a point of inflection. Or vice versa. You're like, I want it when it's concave up first and then concave down. Well, good for you. So over here, it's concave up, and now it's concave down, yes? At that point is where it changes. So check it out. That's the point of inflection. Mr. Groom, x squared, I feel like this one's always concave up. You're right. So when f double prime is positive, the function will be concave up. And when f double prime of x is negative, it will be concave down. Nice. Yes? Look at it. No? No bueno? It's no bueno? No? No. Alright. Now, Lacey wants to do a hard one. I totally understand where you're coming from, by the way. I'm going to go to the Desmos.com and just try to type one in, make something interesting show up. Desmos.com. And watch, Mr. Grimm's going to join some crazy plus 3x cubed. No, that's squared, stupid. Oh, plus e. Oh, I don't want to do e. Maybe I will do e. No, I don't want to do e. That's stupid. Here, let's start off with the nice easy one. Here, go away. Plus 1. Yay! Cool. Screw. I don't feel like this thing ever has a maximum or minimum. Does it look like it has a maximum or minimum? I can't tell for sure. But does it change from being concave down to being concave up? It does indeedy. So let's write that down. Everybody got that down? X squared plus 3x cubed plus 1. Does it really matter what the plus 1 is doing for me here? Not really, because f prime is going to give me 2x plus 9x squared. Here's just a for fun. Could I set it equal to 0? Lily, I think I could. And Lil, furthermore, I'm pretty sure I could factor an x out of both of them. Are you with me? That make sense? And so I feel like when x is 0 or negative 2/9, my derivative is equal to 0. Well, that's weird. That means I have a maximum and a minimum. One's one and one's the other one, yes? Now before you go, which one's which, Mr. Groom, I'm going to do this. I'm going to plot them on a number line like so, yes? Focus your attention on this little fella right here. 9x squared plus 2x. That's a parabola that opens up or down? Huh. So if these are at zeros, it must do this, yes? Meaning that I had positive slopes over here and then negative slopes. Wait a minute, if it was positive slopes and then negative slopes, this guy here has to be a maximum because it was going up and now it's coming down. But this guy, they were going down and now they're coming back up. This guy must be a minimum. Interesting, let's go look at the graph. What if I zoom in a little bit? And what if I touch the graph here? In there. What does it tell me? It tells me where the maximum and minimums occur, yes? They occur at 0, x equals 0, which is what we said, and x equals negative 0.2222, aka 2/9. Yes? Beautiful. Now, where does it change from being concave up to concave down? Somewhere between those two. Okay. Anybody want to take a wild stab at it? 0 and negative 2/9. Anybody want to take a stab at where it would be? Oh, negative 1/9. I don't know. Let's find out. Let's find the second derivative, shall we? So 2 plus 18x equals 0. Whoa, shut up. Look at that. Negative 1/9. Nice. 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 And so the question then is, did it change from being concave up to concave down? I don't know. I know this. F prime of negative 1/9, I know that equals 0. That's the whole point. But here's my question to you. F prime of negative, let's say negative 1. What would happen if you put negative 1 into this guy? Would you get a positive or a negative number? Negative. That means it is concave down when x is less than negative 1/9. And of course, if you were a betting man, my guess is it would be concave up when x is greater than negative 1/9. But again, plug 0 in here, you get positive 2, yes? Right. And so, let's go see if that's true over here. Oh my gosh, it is concave down, now it's concave up. What do you know about that? Nice. Now don't peek at this graph. I'm going to make a new one. But I don't want you to see the graph first. This next one, you are not going to be allowed to graph it. This one I want you to just think about. So let's see if I can come up with one that's kind of gross. Oh, I don't want to do that. Oh, sure. Yeah, that'll be good enough and gross enough. So I want 2x to the 3/2 plus 3x squared e to the x and let's see what you think about this fella. So let's find out where it's increasing and decreasing first. And where is it concave up and where is it concave down? In other words, does it have a point of inflection? I don't know. So first things first. F prime of x would be what?
To the 1/2 plus 6x.
6x plus product rule. Derivative of the first times the second plus the first times the derivative of the second. Totally digging that. Awesome. Oh my gosh, how am I supposed to solve this? Very carefully. Very carefully. Now, okay, you cannot peek at my graph. I'm going to delete my graph. I don't want you to see my graph yet. Now, I will allow this. So is it 3x to the 1/2? I'm going to type it into Desmos. 3x to the 0.5. What's the rest of it? Plus. Cool. So here it is. Clearly you can see that. So what I'm doing is I'm graphing the whatcha-schnutcha. Wow. Yeah. Wow. I don't think, Mr. Groom, that guy's ever coming back. Do you? Well, let's think about this for a minute. If you have this function, 3x to the 1/2, is that always positive? Is this always positive? By the way, when x is what? Bigger than 0, yes? So yeah. And so is this ever going to equal 0? It looks like my function is always increasing. Always increasing when, because why? When x is greater than or equal to 0, because why? Because this guy, my first derivative, is always positive. Right? What about the second derivative? Well, that would be 3/2 x to the -1/2. Oh yeah, cool. Let's do some more product rules. Yay! So 6e to the x plus 6x e to the x plus 6x e to the x plus 3x squared e to the x. I know. I feel like that too. And I feel like I could take a 3e to the x out. Right? And you're like, how am I supposed to solve that? Let's graph it, yo. So what did I say the answer was? So 3/2 x to the -1/2. And then what? Plus 3e to the x times, what was it? Oops. What?
Times 2 plus 2 to the x plus x squared.
Oh, very cool. Very nice. Zoom out a ways. Oh, look at that, Mr. Groom. That's pretty cool. What are those purple lines there? I'll tell you what they are. They're always positive. They're always positive. So wait a minute, Lacey. It feels like my original function was always increasing because the first derivative is greater than 0, yes? And my second derivative is also always greater than 0, yes? Wait a minute. If it's never equal to 0, is there a point of inflection? No. In this case, the sucker must be what? It must be always concave up. So, the original function was what? Read it to me. What was the original function? 2x squared? I forget what I wrote. What was my original?
2x to the 3x.
Oh, that's right. 2x to the 1.5.
Plus 3x squared.
Dude, look at that sucker. Mr. Groom, does it have any minimums? No, it's always increasing. Does it have any points of inflection? You know it doesn't have any points of inflection. No.
Because it has a starting point, which technically is like the lowest point.
Okay, different story. Minimum by definition, that's a good question. That's a fabulous question, sir. Fabulous question, sir. Something we're going to learn in the next couple of days is the extreme value theorem. It is literally the easiest thing you will ever learn. Literally. I'm not joking. I kid you not, Lil. I know you think I am, but I'm not kidding. Hey, look, here's a function. And I'm going to draw it such that it exists between A and B. It is continuous. Mr. Groom, where will the maximum occur of this function? Well, I'll tell you. It'll either be at one of these places where the derivative equals 0, or it'll be at one of the endpoints. On the function we just did, where was the minimum? At 0. Where was that? Oh, one of the endpoints. Nice. But Mr. Groom, what if the function looked like this? The minimum would occur here, yes? At one of the critical points where it equals 0. The maximum would occur right there. What if it was a linear function? Cool. Max, min, done. Okay? Done. Wow, look at that. I just taught the extreme value theorem. It took about 2 seconds. Why is it important that continuous functions be only used there? Well, let's think about it. If you had the asymptote, okay? How high does it go? Forever. Up. How far down does it go? Kind of forever. So that's kind of weird. It's kind of weird. It didn't have to touch every point. It could have jumped up from all the way to infinity, and you're like, that's strange. Continuity is kind of a big deal. Okay, so it must be continuous on that interval, and so it'll either be at one of the critical values where the first derivative equals 0, or it'll be one of the endpoints. Yay! Literally not hard. Now, tomorrow, you're going to be watching a video regarding, oh, that's right, derivatives of trig functions tomorrow. We talked about them a little bit, so it shouldn't take you very long, and then you'll have time to work on both them and this higher derivative stuff tomorrow when I'm not here. It's muy buen and fácil and all that crap. It is very easy. You gotta love it. It's so easy. By the way, if you are not finding that calculus is funner, better, awesomer than pre-cal, you're doing it wrong. Because it's better. No. I like Hawkins a lot, but in calculus, it was yesterday he just got like a 97% on his diffie-q stuff. The concepts and the carrying through get easier as they go on. It gets messier to some degree, but the concepts get easier because after a while, as I mentioned, every problem, what should you do? Take the derivative. Later on, it'll be do an integral. All right, but until then, it'll be take a derivative. I don't know what to do. Take a derivative then. What do I do with the derivative? I don't know yet, but take a derivative. That's a good place to start. If you see anything with 2 dashes, take a second derivative. Okay, that was hard. Okay. Because that's where the fun begins. We're going to start really getting into this stuff in the next, we're getting into the meat of this stuff. So we're going to analyze functions quite a bit. We're going to talk about how things are changing. Interesting to note that if you took a second derivative, we mentioned this previously. Here's my original function. Whee! And Connor said, let's graph from here and here. And these are positives and then negatives. Notice that the biggest negative slope is right there. You see that? And so forth. Check it out. What is also right there? Point of inflection. Right? Point of inflection right there. Yes? And where does that point of inflection occur? Well, this is the first derivative. The second derivative, right, will have a minimum, right? We'll have a 0 right there, won't it? Well, when the second derivative is equal to 0, you have a point of inflection. But where does that happen? It happens where the first one is the steepest. That's where it will change, right there. That always it's darkest before the dawn kind of thing going on. Nice. That's it. So we'll explore this quite a bit more in the next week or so. You're going to get to the point where it's like, this is so easy. But listen, first and second derivative, that's pretty much all we're going to do. Pretty much all anybody does. Later on, we will do a few second and thirds when we get into doing Taylor polynomials. There. I pulled it out of my hat. I did it. Good for me. When we do some Taylor polynomials later, we will do some of that.